we're going to take a look at two more examples of division into cases, one of which is just simply integers, and the other of which is integers but using the quotient remainder theorem. Prove that the sum of four consecutive integers is even. So we know that the sum of four consecutive integers is x plus 1 plus x plus 2 plus x plus 3. Right? So we have to make sure that we understand what we're actually asking. We're saying, okay, well, is that even? Well, we can use division into cases because for any integer x, we could just say that if it's even or if it's odd, we could just show that it fits the form 2p. All right, so here's our proof. Let's start by saying that let's let x be an element of the integers. And of course, we're going to say such that x is arbitrary but particular. So we can use division into cases. We can say since each integer is even and or odd, we can use division into cases. All right. So those are our two cases. All right. And now we know our strategy of approach, even though my handwriting is pretty awful on the screen. All right. So case one, similar to what we did before, we're going to start by the even case. Let's let x be an element of z even. Right? So defining x as z even, so we're going to let x be an element of z even. By definition of even, we can say that x is going to be equal to 2n, where n is an element of the integers. By substitution, we could say that x plus 1 plus x plus 2 plus x plus 3 is going to be equal to 2n plus 2n plus 1 plus 2n plus 2 plus 2n plus 3. And now we're just going to do a little bit of polynomial addition. Okay, so by addition, this is going to be equal to 2, 4, 6, 8n. And then we have 1 plus 2 plus 3 is going to be 6. Okay, and that's by polynomial addition. We can factor a 2 out of this, and we'll be left with 4n plus 3. So remember, every time we want to verify that something even, it has to be of the form 2p or 2 times an integer. So it's by factoring. And we know the trick at this point is that this could be written as p. And p is going to be an integer by closure. All right. And so we've proved that the sum of 4 consecutive integers is going to fit the form 2p. Okay, so thus x plus 1 plus x plus 2 plus x plus 3 equals 2p and is even by definition of even. Right. That's case one. All right, and case one, again, is self-contained. We didn't have to go outside to be able to verify anything. Now we have case two, and case two is the odd case. Okay, so x is an element of z odd. So we're going to define x to be an odd integer. So let's let x be an element of z odd. And by the way, just to kind of make sure everybody understands why we're not doing the arbitrary but particular business. Remember up here, all the way at the beginning, that we stated that x is arbitrary but particular. So that means down here, x is just z odd, and we already have defined it as arbitrary but particular. So we don't have to write that every single time again. So just making sure we understand why we're not doing it each of the different cases. We know by definition of odd that x is going to be equal to 2n plus 1, where n is an integer. By substitution, and it's going to be a long one, but that's okay. We know that x plus 1 plus x plus 2 plus x plus 3 is going to be equal to 2n plus 1 plus 2n plus 1 plus 1 plus 2n plus 1 plus 2 plus 2n plus 1 plus 3. Now we're just going to go ahead and do some polynomial addition. Again, we're going to get 8n, and then we're going to end up with 1, 3, 6, 10. So we just add the constants together. That's going to be 1 plus 2 plus 3 plus 4, which is 10. Okay, so that's by our polynomial addition. And then just like we did before, we can factor out the 2. Okay, so that's our factoring. And then finally, we know the trick at this point, that this is just going to be some integer p. So that's going to be 2p, where p is an integer. All right, so we can't forget that every time we introduce a new variable, that we have to define it as some sort of numeric type. Okay, and that's by closure. Right, and we're done. Right, so what we're going to say is that thus x plus 1 plus x plus 2 plus x plus 3 is equal to 2p and is even by definition of even. And then finally, we can say by case 1 and case 2, so therefore, by case 1, case 2, that the sum of 4 consecutive integers is indeed even. Okay. All right. So let's take a look at one last example. And this time we're going to use the quotient remainder theorem. So this is a pretty cool one if you're a computer scientist, because this is a way to verify if a number is a square, a perfect square, because every integer has the form 3k or 3k plus 1. So we know that if an integer such as 27, which is equal to 5, or I'm sorry, 3 times 5 plus 2, right, has the form 3k plus 2, which means it's not a perfect square. All right, so the square of any integer has the form 3k or 3k plus 1. So if you're writing a computer program, you could do a modulus function, see if the remainder, if modulus 3 is 2, and if it is, that means that it's not a perfect square. All right, so think of any number that fits the form 3k plus 2. For example, 2 is not a perfect square, 5 is not a perfect square, 8 is not a perfect square, 11 is not a perfect square. All right, those are all numbers. So any number that's in the form 3k plus 2 is not a perfect square. But we need to prove that these values, 3k, 3k plus 1, they are perfect squares. So we're going to use the quotient remainder theorem. So that's one use of the quotient remainder theorem is in computer programming, you can use it to eliminate possible values. So anyhow, here's our proof. Okay, so let's let n be an element of the integers, and we're going to say arbitrary but particular. And I guess we should say n is arbitrary, or where n is arbitrary particular, just to be precise about this. And we know that the quotient remainder theorem. So by the quotient remainder theorem, so we're not using even or odd on this one. Okay, I gave you the hint to use the quotient remainder theorem. So by quotient remainder theorem, with d equals 3, there are 3 cases, right? And you might remember we actually did this problem at the very beginning of this section where we started defining all the different outcomes for the quotient remainder theorem. So the 3 cases is that n is going to be equal to 3q plus 0, n is going to be equal to 3q plus 1, and then n is going to be equal to 3q plus 2, where q is an element of the integers. Right? So what we've done is we've defined our variables, and then we've gone through and defined all the different cases. So we're going to have 3 cases. Right? So case 1, and remember what we're doing is we're trying to show that the square of any integer is either 3k or 3k plus 1. And these are our 3 integers that we're squaring. Okay, so case 1 is going to be n equals 3q. This is probably the easiest case. Okay, so we're going to say let n equal 3q, where q is an integer. Okay. By substitution, remember we're squaring the integer, n squared is equal to 3q quantity squared. And then we're just going to do a little bit of algebra here. So that's going to be equal to 9q squared, and that's just by exponent rules. Okay, so that's our exponent rules. We need to show that it fits the form of either 3k or 3k plus 1. So it's pretty easy to see that it's going to be 3k because we can factor off a 3. Okay, so this is by factoring. And then finally, this is going to be equal to 3k, where k is an integer, by closure. Okay? And so what we can say is, hence, n squared equals 3k, and case 1 is valid. All right. Now, case 2, a little bit tougher, but not too bad. Case 2 is going to be the case where we're going to say that n is equal to 3k plus 1. So, or n is equal to, 3, not k, because we're eventually trying to get to k, but let's call it 3q plus 1. All right, so let's let n be equal to 3q plus 1, where q is an integer. Right? Again, by substitution, we can see that n squared is going to be equal to 3q plus 1 squared. We're going to FOIL this out, all right, because remember, this is going to be 3q plus 1 times 3q plus 1, and that's going to be equal to 9q squared plus 3q plus 3q plus 1. Okay, so that's just by multiplication. Right? And that's going to be equal to 9q squared plus 6q plus 1. We can factor a 3 out of the first 2 terms. And that's going to leave us with 3q squared plus 2q plus 1. Right? So this is by like terms, just polynomial addition. This is by factoring. And then we can just use the closure trick where this is going to be 3k plus 1, where k is in z, right? And it's by closure of integers. And so we can say thus, n squared equals 3k plus 1. And remember, that was one of the 2 cases that we were hoping for. So we go all the way back up here, and it's of the form 3k plus 1. So we're done with this. And by the way, remember, we have to show, even though n started out as 3 times an integer plus 1, we had to show that the square of the integer was of that form. All right, so we can't just immediately jump to the conclusion of that. Okay, so thus n squared equals 3k plus 1, and case 2 is valid. Right? So finally, we have our case 3. So now case 3 is going to be the case where n is going to be equal to 3q plus 2. And we're going to require a little bit more algebra to be able to do this one, but not too much. So we're going to say that we're going to let n be equal to 3q plus 2, where q is an element of the integers. By substitution, we can say that n squared is going to be equal to 3q plus 2 quantity squared. We're going to FOIL it out. All right, so just like before, remember that this is 3q plus 2 times 3q plus 2. All right, so you can't just say 9q squared plus 4 unless you want to be wrong. So this is going to be equal to 9q squared plus 6q plus 6q plus 4. All right, and that's just by multiplication. We're going to combine like terms. 9q squared plus 12q plus 4. Okay, so that's by like terms. We need the form either 3q or 3q plus, or 3k or 3k plus 1. Unfortunately, it doesn't look like 3k is going to be valid. Right? What about this 4? Well, we can split off a 3 and we can use computation, and we can rewrite this as 9q squared plus 12q, and instead of 4, we can write that as 3 plus 1. Right? And so that's our computation. And we can do a factorization of 3. So 3q squared plus 4q plus 1 plus 1. So that's by factoring. And then finally, we can just rewrite this whole animal right here as p, or k in this case, because we need to fit the form 3k plus 1. And so that's going to be 3k plus 1, or k is an element of the integers. Right? And that's by closure. Right. And so we're done. So case 3 is valid. So thus, we could say n squared equals 3k plus 1, and case 3 is valid. All right. So finally, by case 1, case 2, and case 3, what we can say is that we can go all the way back and we can say the square of any integer is of the form 3k or 3k plus 1. All right, so, and again, we want to verify that for uses in computer science, and there's a number of other different ways or other uses of the quotient remainder theorem. This is just one of the more simplistic. All right, so as we've seen, division into cases takes a long time to do, but it's not too terribly awful with respect to higher level brain power. All right, so in the next section, we're going to start taking a look at div and mod, and then we're also going to start taking a look at floor and ceiling functions.